What will be the linear momentum for the system if there is no net external force on the system? What will be the momentum? Constant. And constant means the same. So it means that P initial is equal to P final, which is equal to constant. And this is what we call, this is the summation of momentum. The law of conservation of linear momentum. Law of conservation of linear momentum. Momentum conserved. The linear momentum conserved. This is the third fundamental law of nature we are learning here. What was the first? Which I explicitly, we use it, but we never say it in physics. I just said in chemistry, use very frequently in chemistry. What is the first thing you know that conserves? The single thing, mass. The law of conservation of mass, first fundamental law of nature, conservation. The second fundamental law of conservation was the work energy theorem, or the energy conservation theorem, 1 and 2 and 3, that we used before in the previous topic. And now, the third conservation law is the law of conservation of linear momentum. Under what condition the momentum conserved? What have to happen in order for the momentum to conserve? What is the condition or assumption I make there? No external forces. So when the momentum will conserve, here in this situation, look. So you can see here. So the momentum conserved. These two objects, this object is at rest. This object is moving. It will be moving, right? If there is no net external force, assuming that the friction is negligible, what will happen? The momentum of this has to transfer to this one. Is that correct? So look. So I give velocity to this, right? It's not moving, and this will be moving. What happened to this one? This top. So means that the momentum at the beginning was transferred to this one because they have the same masses. Got it? So the momentum conserved. And this is the law of conservation of momentum. This is assuming that the friction is negligible, which it is. Now, if we put two objects in this situation, if I put two objects and this is moving, when we have two masses, then you can see that the velocity reduced to half. Right? Why? Because they stick together. So as a combination, the mass gets reduced. If this was not moving, the momentum of this then have to be the momentum of both together. And you can see that the velocity of this object gets reduced to almost half. The momentum again conserved. So this is this law of conservation. Now, there will be two types of collision. And we will just, I'm talking about the theory first a little bit, and then I will move to the solution of problem. Collision. There will be two types of collision. We will be interested here. Two types of collision. Number one, inelastic. And number two, elastic. In what they will be different? We will see. Inelastic collision is when there is transformation or change, the way that we will see when the collision between two objects will be inelastic. The way that you can see physically is when the two objects collide and there is a change in the structure from the original one in any of the two objects. If you see a deformation of the object, that collision will be inelastic. For example, if these two objects collide, how can you see or how can you feel that the objects are not the same, the structure is not the same, somehow it's something different. When they stick together, what do you think that happened between them? This is a Velcro here, right? Do you think that will be the same shape of the Velcro before and after the collision? No. Is this collision elastic or inelastic? Inelastic. You throw a ball to the wall, and the wall suffers. You see like a mark, a dent on the wall. And maybe you don't see the ball, but you see a dent on the wall. Is that elastic or inelastic? Inelastic. Two cars collide on the street. One bumper to one side, the other to the other side. What type of collision is that? Inelastic. You throw a ball, tennis ball, to the wall. Let's model like it. And the ball rebounds and regains the original shape. You don't see any deformation on the wall. And the ball regains the original shape. What type of collision will be that? Elastic. This is the difference between elastic and inelastic physically. The way that we will see mathematically or physically from the physics point of view, I will talk later. Now, in this particular case, now these two objects here barely get touched. You can see they barely get touched. Can you see? Why? In this case, because there is a magnet. I am just faking this. But barely get touched. What do you think? Is there any deformation in the objects? No. So you can see that barely there is a deformation. So since there is no deformation, probably this collision, if we think as a collision, will be elastic. So the inelastic and elastic, what happened physically speaking? Because this is a fundamental law of nature, Pi will be equal to P final. Here, Pi is equal to P final as long as the net external force will be zero. Good. On the second case, the mechanical energy here suffer a change. It's not equal to zero. If it's along X, which there is no potential energy, delta K will be also different from zero. And this amount of kinetic energy change is what we will call thermal energy. So, when two cars collide and you touch the bumpers, how do you think that the bumpers will be? Half. That energy that is there is the amount of changing kinetic energy between the two cars. Before the collision and after the collision for the two cars. If you are able to find the change in kinetic energy, that change in kinetic energy will be the heat generated during the collision. On the other side, Pi will be equal to P final, but there is no change in mechanical energy. EI